During the previous demonstration, we saw how lax system administration policies and practices allowed an external attacker to infiltrate a machine in Loudacre Mobile's Hadoop cluster. In this demonstration, we'll look at some of the steps that the company system administrators might take to improve the security of their systems in order to prevent, or at least detect, certain types of attacks. One of the first things you can do to help secure the nodes in your cluster is increase system entropy. This is essential for many security-related functions on the cluster, including the processes of creating encryption keys or generating secure passwords. You can check the amount of entropy available on a Linux system by looking at the current value in a special file within the proc virtual file system maintained by the kernel. In this case, the system only has 136 bits of entropy, far less than the minimum of 500 that we want to have on a production server. On most Linux systems, including Red Hat Enterprise or CentOS, you can increase entropy by installing and configuring the RNG tools package. You need to do this on every node in your cluster, although we'll demonstrate the process here on just one node. However, if the package available for your operating system provides RNG tools version 3 or lower, as would be the case for Red Hat Enterprise 6.6 and earlier, then you'll need to build a newer version from source code to ensure proper operation. That's necessary because older versions didn't properly integrate with the hardware-based random number generators found on modern server-class Intel CPUs. In this case, the cluster is running CentOS 7.2, so I can simply install the package available in the yum repository. Next, I need to copy the default systemd unit file to the proper location under the etc directory so that I can customize it. Now, per the instructions on Red Hat's website, I'll add the startup options to define the paths used by this service. I'll run the systemctl daemon reload command to set up everything necessary for systemd to run the daemon. Then, I'll check whether the service is configured to start automatically when the server boots up. I see that it is set to start on boot, so I'll just use the systemctl start command to launch it during the current session so that I don't have to reboot. Now that I've installed and configured the service, let's check the available entropy again. We can see that we have 3,166 bits of entropy available. Remember that we want a minimum of 500 bits, but more than that is even better. Again, these steps must be repeated on every node in the cluster, but I'll do the others off camera before moving on to the next part of the demo. One of the failures that led to a Loudacre mobile server being compromised was a weak password that was easily guessed using a password cracking utility. One way to make these attacks less likely to succeed is to enforce a system password policy that prevents weak passwords. On distributions based on Red Hat Enterprise Linux 7, such as the one this cluster uses, the minimum standards for password quality for a host are defined in the pwquality.conf file, which is located in the etc security directory. Older releases or other distributions may use a different location for that file, or they may use a different mechanism altogether, so you should consult your vendor's documentation for details on your system. In this case, I'll define the standard to require at least 4 character classes, which means that a password isn't valid unless it has one or more lowercase letters, uppercase letters, digits, and punctuation characters. The default policy also requires a minimum of 8 characters. Now, let's test this out by opening a new terminal window and connecting to that node through a secure shell session using the support user account. After logging in, I'll first try to change the password to secret, which fails because that 6-character string is shorter than the length required by the default policy. Next, I'll try to change the password to secret123, but this fails because it doesn't meet the min class requirement. It contains just lowercase letters and digits. Finally, I'll change the password to a series of characters that does actually meet the requirements. As you can see, the system accepts the new password. Sometimes it can be a challenge for users to come up with good passwords, particularly when stringent policies are in effect. One solution for this is to use a program to generate a password for you. The pwmake utility available on most Linux distributions offers a convenient way to do that. It uses the system's dev random file to generate a password with a specified amount of entropy. For example, if we run this command with an argument of 64, it will generate a password with 64 bits of entropy. Let's compare some passwords generated with different amounts of entropy. The man page for this command advises that 64 is adequate for most applications, while a password with at least 80 bits is a better choice when an attacker has direct access to the password hash. The password hash can be found in the etc shadow file on a typical Unix or Linux system. I'll generate another password using an argument of 80, and then I'll use that to set the password for the support account. Now that I've improved the password policy on the host, I'll disconnect from this secure shell session and close the terminal window. Then, I'll return to the root shell on the worker node so that I can demonstrate how to set a password aging policy. This will ensure that users change their password at regular intervals, which in turn limits the effective window for attempts to crack them. The chage command, which I'll pronounce as change age, allows the administrator to view and modify attributes related to password expiration. For example, I can display the current settings for the support account using the changeage-l support command. Running that command without any options begins an interactive session where you can set the password aging policy for the specified account. I'll set a minimum password age of 2 days, a maximum password age of 90 days, and a password expiration warning of 10 days. I've chosen a warning period that's a bit longer than the default of 7 days so that an employee still has a few days warning if they're away for an entire week. You can also use command line options to achieve the same result. I'll run the first command again to illustrate the effect of our changes. There's no way to set a global aging policy for all local users on a Linux system. You must make changes on a per-user basis, although you can use the command line options shown earlier for scripting the process of changing multiple accounts at once. However, the etc-login.defs file allows you to set certain options, including those that affect the password aging policy, for any new accounts created. I'll edit this file now, so that all new accounts on the system will have the same policy I've already set for the support account. After the attacker infiltrated the system, she was able to elevate her privileges to gain root access by exploiting the system administrator's insecure, homegrown backup script. As you may recall, the administrator wanted to delegate the ability to back up any file on the system to the support staff. Although that's a reasonable goal, the administrator did this by enabling the setuid bit on an executable that ran a shell script. This was an ill-conceived workaround for the fact that Linux systems prevent you from enabling the setuid bit on shell scripts directly, which is a rule enforced precisely to avoid the type of breach that occurred here. Setuid binaries can present a security risk, but some important programs, including a few of those in Cloudera's platform, require setuid for normal operation. The fact that a binary has this bit set isn't necessarily a problem by itself, but system administrators should watch for any new ones that appear, particularly those in users' home directories and other unusual places. In this case, the bigger problem was that the setuid binary invoked a world-writable shell script. That means that any local user could edit it and add code to run any program with root privileges, as the attacker did by launching a shell. By setting up a setuid binary that invoked a world-writable script, the system administrator created a security hole that the attacker was all too happy to exploit. Let's look at how we can scan the system for setuid and setgid binaries, particularly those in user directories, which are more likely to represent an unnecessary security risk. Vulnerability assessment scanners used for routine system auditing are often configured to search for and report setuid and setgid binaries, but you can also easily do this with a find command in Linux. Unix utilities that deal with file permissions, including the find command, accept either a symbolic value, such as X for execute or W for write, or a corresponding octal numeric value, such as 1 for execute or 2 for write. The setuid and setgid bits also have both octal and symbolic values. These precede the set of bits you'd use to specify the user's permissions. The setuid bit has a value of 4. The find command in Linux supports a perm option that enables you to locate files based on their permissions. If you specify an exact mode as an argument to the perm option, it will only show files and directories with exactly those permissions. However, if you prefix the mode with a dash, then the command will show files that have the specified bit set. For example, by prefixing the mode 4000 with a dash, it will match any object with a setuid bit enabled, regardless of whatever other bits might also be enabled. The numeric value for the setgid bit is 2, so this command will find anything below the home directory with a setgid bit enabled. If both the setuid and setgid bits are enabled, the values add up to 6, so this command will search the home directory for objects where both are enabled. The previous search effectively used an AND condition. It only showed matches where both bits were set. You can change this to an OR condition by replacing the dash with a slash. This command will search the home directory and match any object that has either the setuid or setgid bit enabled. We can combine this with additional options to narrow the search. This command will search the home directory and match any object that has either bit enabled and is owned by root. And finally, this command will do the same thing, but it will also display the permissions associated with each file it finds. We see here that the file it found has the setuid bit enabled and is executable by any user. Fortunately, the only file we found is the one we already knew about. Loudacre has just hired an experienced new system administrator whose first task will be to remove that and set up a better solution for backups. Therefore, we'll now look outside the home directories. This command will check for setuid and setgid binaries below the user bin directory. As I mentioned earlier, these bits are necessary for certain applications to function normally. The fact that some binaries on your systems have them enabled isn't necessarily a problem, but you should know their origin and evaluate whether they are legitimate and necessary. Let's look at how to do that. One of the files identified by the find command is user bin locate. You can discover the source of this binary by querying the package manager. The command shown here will identify which package was responsible for installing that file. If the file is owned by a package, as this one is, you can then check the description, origin, and other details of that package. You can also run a command to see the other files that were installed by that package. Since most files in the user bin directory have a corresponding man page, reading that can give you some background on a program you don't recognize. These techniques are usually enough to let you see where a file came from and whether it has a legitimate purpose on the system. In this case, it's part of the Linux distribution and is a legitimate file with a legitimate need for the setuid bit. However, since its only purpose is to allow you to search for any file in the machine by name, it's not really essential for the operation of a Hadoop worker node. One way of reducing the attack surface is to eliminate unnecessary programs. After all, an attacker can't exploit something that isn't there in the first place. I think the convenience of being able to quickly locate files does not justify the risk associated with this package, so I'll remove it. Not everything will be owned by a package. For example, some files added to the system from parcels or created by Cloudera Manager will not be owned by a package. That's the case with the Hadoop command in the user bin directory. Let's look at some steps you could take to determine the origin of that file. The first step is to list all the details, which shows us that it's a symbolic link to a file in the etc alternatives directory. The operating system provides this file as a way to support having multiple variants of a software package installed on the system at the same time. I'll do a long listing on the target of that symbolic link. This shows the real path to the file, which gives us a hint that it's part of CDH. Finally, I'll query the package manager to see if this file is part of an installed package. It's now clear that while user bin Hadoop was not provided by an operating system package, it is part of the CDH installation on that machine, and we can infer from the path that it was added through a Cloudera Manager parcel. Knowing what software is installed and where it came from is important for security. CDH, whether installed through a package or parcels, creates a number of symbolic links on hosts that point to version-specific file names using generic names for more convenient access. We'll now look at how you can use the auditing framework that's available in more recent Linux distributions, including those based on Red Hat Enterprise Linux 7. This system can collect details about a variety of security-related events, such as failed logins or the execution of certain commands, and provide search and reporting capabilities based on that information. Before I can use it, I'll need to make sure that it's running on this system. Great, it is running. I'll generate a report based on the information the system collects by default. We can see that there's an excessive number of failed logins and authentication attempts relative to the total number of those types of events in the report. This is a cause for concern, so let's investigate it. The AU report command has a lot of options, so it's helpful to look at the man page when you want to learn more about them. The auth option will provide additional information about the failed authentication events, but there are also many others that you could use to investigate other areas of concern. I'll run the same AU search command I ran before, only this time I'll add the auth option described in the man page. The lines of output between the rows of equal signs are column headers. Although the columns don't really line up here, I can still identify fields based on their position. For example, the record number will be the first field, the date will be the second field, and so on. The success field is at position 8, followed by information about the event. Since there were more than 100 events, I'll use the / command to search for records related to the secure shell daemon, and in particular, those with a success field value of no. The man page also described an option that filters the results to show only failed attempts, but the method I'm using will allow me to see failures alongside successful attempts, which provides some context that will help me to distinguish a user who carelessly types a password once or twice from a brute force attack that repeatedly tries a series of passwords in quick succession. As I page through the results, I can see a long series of failed authentication attempts for the support account, starting at line 132. There were more than 20 of these in less than a minute. In fact, the ones toward the bottom indicate a rate of about 5 per second. This is faster than we can expect a human to type, and so it's a clear indication of an attacker attempting to guess passwords for an account on this machine through brute force. Without regular system auditing, this incident may have gone unnoticed. I can use the AU search command with a -X option to display all entries related to a specific executable. Here's an example showing information about the C02 command. Adding the -I option to the same command makes the output easier to interpret. For example, the numeric user IDs are now replaced with the corresponding usernames, so we see root listed in the output instead of UID 0. You can control what types of events are logged by adding or removing rules in the auditing framework. This is done with the auditctl command. One basic type of rule is called a watch, which is so named because it watches for changes to a file. To add a watch, invoke the command with the -W option, followed by the path of the file to monitor for changes. By default, this will create events whenever the file is read, written, executed, or has its attributes changed. To be clear, this doesn't track the actual content of the changes, as revision control systems like Git or Subversion would do. It just keeps a record of the system calls that are used to access or modify the file. I'll demonstrate the syntax by temporarily adding a watch for the etc password file. To remove a watch, use the same syntax as for adding it, only this time change the W option to uppercase. I'll demonstrate this by removing the watch I just added. To make it easier to search for rules, particularly more sophisticated ones, you can tag them with the name of your choice. Since this is a demonstration, I'll use the tag demo to show how this works. I'm running the same command as before to add my watch on the etc password file, only this time I specify the -K option, followed by the name of the tag I want to assign to those events. I'll generate an event with that tag by changing the comment field for the support account in the password file. Now I'll use the AU search command again to search for events associated with the demo tag. As you can see from the output, there are some events with that tag. The ID for each audit event follows the colon that's shown just after the timestamp. In fact, there are 3 different events. That's because edits to the system password file are actually handled through a file locking scheme that involves making a copy of the file, modifying the copy, and then replacing the original. By default, watches are triggered by both read and write operations, so the update results in multiple events being generated. For this explanation, let's just focus on the one at the bottom. Each event contains 3 records, each of which is shown on a separate line, but they're all long enough that they wrap around in the terminal window here. The first record identifies the path of the file for this event, which you can see as the etc password file. The second identifies the current working directory used by the process that invoked the system call. The third is the system call that triggered this event, which in this case is a system call to open the file. Now that you've seen the basics of an audit rule, I'll briefly demonstrate a more sophisticated example. This command will record all system calls related to the execution of the backup script. The first command line option specifies that we want to log system calls as they exit. The next defines a filter for the rule to monitor the file at the specified path, while the one that follows indicates that we want to track all system calls. After that, we add a filter based on the types of operations that will trigger an event. In this case, attempts to read or execute the file. The next option defines a filter based on the audit user ID. Note that this is based on the user's identity upon login, not the one they may have had at the time the command was executed, which would be different in the case of a command executed using the su or sudo command. The value we use here filters out the large unsigned number that audit-d uses to indicate an unset value for the login UID, so we're only selecting actions by users who didn't log in directly as root. We enclose this argument in quotes to prevent the shell from interpreting the meta characters it contains. Finally, the last option assigns the backup tag to these events so that we can easily find them with AU search. With this rule in place, I'll trigger it by first logging into the worker node as the support user, then changing to the backup directory, and then running the insecure backup script exploited by the attacker. This should trigger the rule. I will now return to the original terminal window so I can search for the event generated by running the backup script. We can ignore the first line in the output, which just indicates that we changed the audit system configuration by adding the rule. The combination of the path and CWD records tells us that the event relates to the file named mybackupscript.sh in the home support backup directory. The final record tells us that the open system call triggered the event and that the user bin bash command was executed, which is typical for invocations of a shell script. The interesting part of this event is the difference between the user ID, found in the UID field, and the effective user ID, found in the EUID field. Putting this all together, we can see that the shell script was executed by the support user, but the process that resulted ran as root, which is extremely unusual behavior for a shell script, particularly one found in a home directory. Once again, the audit system has led us to uncover evidence of an attack. Let's look at one more example. In this case, we'll monitor the use of the write command by non-root users, which might be used for social engineering. The command is similar to the previous one, except that I'm using a different tag and I've omitted the R from the perm option because the write command is a compiled executable rather than a shell script. I also included an additional constraint so that events will be generated only when the command is run by users who logged in with a user ID of 500 or more. In other words, regular user accounts instead of special purpose system accounts. Now that I've added the rule, I'll try and trigger it by opening a new terminal window and initiating a write session with the system administrator. That ought to do it. Now I'll return to my original session and search for events with that tag. As before, the first line is an event that merely indicates I've added a new rule. Running the write command resulted in one event. It's pretty similar to the ones you've already seen, although you can see here that the user ID and effective ID are the same, indicating that the user didn't gain any additional privileges when running the command. Because this was a compiled executable, there are a few other differences. For example, we have two path records, one for the user bin write program itself and another for the Linux program that loads the shared objects required to run it. There's also an additional record called execve that holds details about this system call that Linux used to launch the executable. In this case, we can see that the program was used to send a message to the root user. You can see the current set of rules by using the auditctl command's -l option. The rules are transient and will only remain in effect while the system is running. To persist the rules so that they'll survive a reboot, you can include them in a text file in the etc audit rules.d directory. A convenient way to do this is to run the command I just showed for listing the rules and capture its output to a file in that directory. In this part of the demo, I'll show some commands for defining firewall rules that can be used to protect a specific host. Before I begin, I want to emphasize that perimeter security is best implemented by using a dedicated firewall appliance that isolates the network used by the Hadoop cluster from other, unrelated networks. For an on-premises deployment where the cluster runs in the company's data center, you'll almost certainly isolate the cluster from the internet. But you can also limit points of entry for an attack by configuring your firewall to block connections from internal networks for which there's no business need for cluster access. Host-level firewalls complement network firewalls and provide an additional layer of security, since they can be used to further restrict connections to individual services within the cluster. Since this machine is running a distribution based on Red Hat Enterprise Linux version 7, I'll modify the host-level firewall rules through commands provided in the firewall-d package. Older versions use the iptables command to modify rules. The first step is to install the firewall-d package. Now that it's installed, I'll start the service so that I can begin setting up the rules. The firewall-d package provides a command line utility for making changes to the rules used at runtime. Using the --list-all option for this command displays the rules that are currently active. This can be a good first step when trying to troubleshoot connectivity problems. The firewall in this version of Linux supports the concept of zones, which can be used to associate different levels of trust with different networks. For example, someone running Linux on a laptop might define one zone for work, where the connections for most computers on the network are allowed, and other zones used when connecting to a public network, such as the Wi-Fi hotspot at an airport where the other computers on the network are distrusted by default. This is particularly useful for laptops that often switch between different networks. You can use the --list-all-zones option with the firewall command to display the zones currently defined. If your cluster is isolated on its own network, you might define a rule like this to allow access to and from any node in that network. This example shows the rule that you would use when all cluster nodes are contained within the 10.1.2.0/24 subnet. Since this rule, like the other ones I'll demonstrate, relates to setting up a host-level firewall, you'll need to repeat these steps on all the other nodes in your cluster. If you want to control access to and from this machine based on specific hosts, rather than an entire subnet, you can add a source rule that uses the IP address of those hosts instead of a subnet. In this example, I'm allowing connections from 2 specific machines. If systems have multiple interfaces, such as you might find on gateway nodes, you may want to allow all traffic coming in to a specific interface. If you've installed the bash completion package, then you can hit the tab key twice to see the available interfaces. In this example, I'll choose the ETH0 interface. Likewise, you can use tab completion to see well-known services, such as Secure Shell, HTTP, and HTTPS. I'll add a service-specific rule to demonstrate this. After I type HTTP, I hit the tab key twice to see the suggestions for matching services. In this case, I'll choose HTTPS. The tab completion isn't aware of most of the services used by CDH, but you can also add them with specific port numbers. Here's an example of adding a rule for TCP port 7180, which is the one used by the Cloudera Manager web interface. Here's another example of a service-specific rule, which allows connections for the HBase Thrift service on TCP port 9090. The commands I've demonstrated only change the current firewall rules in the kernel, so they'll be lost when the machine shuts down. To save the configuration so that it remains in effect even after reboot, you can make these runtime rules permanent by running the firewall command with the --runtime-2-permanent option.